Let's continue our exploration of design phase by now looking at how we transform the logical specifications that we might have developed in analysis phase into physical specifications. In this process in design phase, we take the kind of logical specs that we made in analysis phase and make actual decisions about how those will be implemented. In some cases, they'll be implemented in software, but you'll see in other cases, we might decide that it's best that a human or physical process take care of some aspects. After this video, you'll be able to map a logical process to physical processes as well as identify a human-machine boundary in the implementation. Finally, you'll be able to read a program structure chart and program specification. Note that as a business analyst, we typically won't be creating a program structure chart or program spec, but it's important that we know how to read them so that we can review and ensure that they're aligned with the requirements we developed in analysis phase. Let's take a look at our inventory of design phase. We're going to look at converting logical processes into physical processes. We'll talk about CASE tools, computer-aided software engineering tools, and their role, and designing the programs that will perform those processes. In earlier videos, we took a look at determining the preferred system acquisition strategy, as well as designing the architecture for the system. And then interface design is typically the domain of a computer scientist or software developer who would know how to make a user interface that is either easy to use or easy to learn. In this video, we'll look at transforming the logical data flow diagram into a physical one, a program structure chart, and creating the program specs. Again, the business analyst role is not necessarily to create these deliverables. Our role is more to read them and make sure that they're well aligned with the diagrams and requirements that we developed during analysis phase. As such, most of the activities will be focused on reading these diagrams, and we'll take a higher level approach in the video. Let's first take a look at converting a logical data flow diagram that we might have developed in analysis phase and how that might transform into a physical data flow diagram. You can see the logical diagram is on the left here. The load website process in the physical diagram on the right has a specific technology, in this case HTML or PHP, that process will be implemented in. The data stores now have specific technologies. So the targeted promotions data store is now a table in a MySQL database. We can also see that the data flows now have specific forms associated with them. In one case, the tune itself may come through as an MP3 file. The idea here is to make decisions about the technologies that we'll be using to implement some of the processes. Again, effective analysis phase diagrams actually don't list these technologies. We wait until design phase to make these decisions. Finally, what you see here is a human-machine boundary highlighted in yellow. The human-machine boundary defines which processes will be performed by humans and which processes will be performed by software in an automated fashion. In this case, the human-machine boundaries surround solely the customer, indicating that most of the processes will be performed by a computer. Finally, you can see that some implementation decisions can be relatively simple. In this case, the D7 data store is simply added as an ASCII file or a simple text file, and so it need not be complex. One logical process might have many different physical implementations. So let's take the logical process on the left, in this case checking our customer credit. You can see we have a lot of options for how we might implement this. We could choose COBOL, Visual Basic, or external software such as QuickBooks. We don't often think about it, but we could also choose a human being. In this case, we could have the accounting clerk do the process manually if we decide that that's best. One logical process has many different physical implementation options. Data stores have options as well. So on the left, you have examples of logical data stores, and on the right, you have examples of physical data stores. We typically don't include a specific technology with the logical data stores. Instead, we make that decision in the design phase. Here we have Oracle, SQL Server, Microsoft Access, tape backups, file cabinets. You can see that the kind of array of options for physical data stores is almost endless. Similar for data flows, we have a lot of options as to how we implement logical data flows in the physical world. On the left-hand side, you have the logical flows, which don't make reference to any technology. On the right-hand side, you have specific technologies such as HTML, a printout, SQL, and so on. Let's next look at a program structure chart. The data flow diagram breaks the process down into sub-processes. Each primitive would have a process description in structured English or a decision table, like we covered in an earlier video. That would then be used to create a program structure chart. In the structure chart on the right, you see the processes from the diagram on the left broken down into a hierarchical structure like you see here. Again, the business analyst is not likely to create the structure chart. This would typically be created by a software developer. However, you might want to review to make sure that all the processes in the DFD are accurately accounted for in the program structure chart. The structure chart, each module is described in submodules or in a program specification. The program spec is a lot like a primitive from the earlier example. However, in the DFD primitive version, we were careful not to make reference to specific technologies. When we make a program specification, we typically do so in a very physically specific manner. So, for example, in processing payments, the specific text that you might see would be very detailed. This is an example of a program specification that you might see in a CASE tool. CASE stands for Computer-Aided Software Engineering. CASE tools often allow you to input very specific logic and instructions. This is then relayed to software developers who can do the final translation step into working software. The deliverable that you see here would typically be reviewed by the business analyst to make sure that all of the processes in the original data flow diagram are accounted for in the physical software. Here's an example of a program spec. You know that this is typically a program spec because of references to things that are very physical. For example, using the open file dialog, a multi-line text box, write a function. These are distinctly different from the kinds of things that we might see in a primitive as part of our data flow diagram compilation. Now, as tools have gotten better over the years, it's kind of created a conundrum of sorts. In this case, many of the newer programming tools, parts of the design are actually completed with the implementation of the implementation phase programming tool. So, for example, we don't often draw physical DFDs anymore. In some cases, the tools that we use, we take the logical DFD and we can actually extract the physical DFD from, say, the program specification. A more typical example is we can take the physical ERD, which we'll look at in a minute, and we can usually extract that from our database design itself, which ultimately was based on the logical ERD we prepared in analysis phase. So, we've looked at converting the logical processes to physical processes using our case repositories. Finally, let's look at a similar conversion from a logical data model to a physical data model. Converting a logical entity relationship diagram to a physical entity relationship diagram is part of a multi-step process. Many steps of the process are covered in other technical courses that you might find on a platform like Coursera. We'll just talk about the process at a very high level and the differences between a logical and a physical ERD. The basic process involves taking the entities from our analysis phase ERD and changing them into tables in a relational database. The attributes become fields, the candidate identifiers become primary keys, we add foreign keys to represent our relationships, and finally, we balance with the physical DFD to make sure that we haven't left anything out. Again, most of these concepts are covered in other more technical courses, in addition to things like database normalization, which we don't really cover here. You can see, though, that the physical entity relationship diagram has some extra components to it. So in this case, we see that the fields often have data types associated with them. We also see that foreign keys are included. So for example, you see the tune ID is included in the tune sales entity. And then finally, we balance this diagram with the physical DFD as a way to double check and make sure that we haven't forgotten anything. Many of you might have already had some exposure to relational databases, even if you've used a simple tool such as Microsoft Access, or maybe more complicated or full-featured relational database platforms such as MySQL, Oracle, or SQL Server. The basic process involves changing entities into tables, changing attributes into fields, adding our primary keys, foreign keys, and then finally balancing with the physical DFD. You can see that all of these processes are performed in a tool called Microsoft Access here at the bottom. With newer database tools, the physical ERD is generally not explicitly drawn. Instead, most modern database tools provide an ability to draw or essentially extract the physical ERD from the database structure that's created using the logical ERD. That wraps up our discussion of translating processes, logical processes into physical processes. Future videos will take a look at implementation phase and the kinds of considerations that the business analyst might have at the top of their mind as we move through implementation phase.